Tonight, we are going to understand what it means to be the size we are in a universe the size this one is. Not the familiar version. Not the Carl Sagan version you think you already know. The version that lands. Most people believe they have already processed this. They have heard the numbers, they have seen the photographs, they have watched the documentaries. They know space is big. They do not know what big means. There is a specific difference between knowing a fact and holding it. Between reading a number and feeling its weight. Between the intellectual acknowledgement of smallness and the actual confrontation with what smallness means at every scale. Tonight the numbers will not stay numbers. They will become something you cannot put back in the abstract box where you have been keeping them. There are 5 layers of scale between where you are sitting and the edge of what we can observe. Each one makes the previous layer disappear. Not shrink. Disappear, reduce it to a rounding error in a larger account. By the time we reach the 5th layer, the first 4 will be mathematically irrelevant. By the end of tonight, you will understand why the word horrifying is the accurate word. Not dramatic, not an exaggeration. Accurate. The word that names what it feels like to face something your brain was not built to hold. If this is what you come here for, subscribe below. It costs nothing. It helps the channel keep making scripts like this one. Now, let us begin. Most people think they already understand how small we are. This is the first thing to address, because if you carry that assumption into what follows, the numbers will slide off. They will feel like confirmation of what you already know. They will not land. You have probably seen the pale blue dot. The photograph taken by Voyager 1 on February 14th, 1990, from 6 billion kilometers away. Earth as a pale speck. A single pixel caught in a sunbeam. Carl Sagan wrote about it. The image became one of the most shared photographs in history. Sagan delivered a speech about the photograph at Cornell University in 1994. The recording circulated widely, and the passage he delivered about the pale blue dot became one of the most quoted pieces of secular writing in the following decades. He described Earth as a mote of dust suspended in a sunbeam. He wrote about how wars, empires, and ideologies had been staged on that pixel, how every human who had ever lived had lived and died there. The image and the speech together produced something, a genuine shift in perspective for many people who encountered them. The smallness felt real in a way that abstract statements about the universe's size do not. Seeing the actual photograph, the actual pixel, the actual sunbeam, collapsed the distance between the abstract claim and the felt experience. But the shift, while real, was partial. It made Earth look small relative to the solar system. The solar system, in that shift, became the implicit reference for what large meant. The rest of the universe faded into background. What the pale blue dot revealed was, Earth is smaller than you thought. What it did not reveal, could not reveal from that position, was the solar system is also smaller than you thought. And the Milky Way is smaller than you thought. And the local group. And Laniakea. And the observable universe is the smallest structure we know of that can be called the universe. The pale blue dot is the beginning of understanding cosmic scale. What follows this script, the image that would show what we look like in context, would require a telescope positioned outside Laniakea, pointed back at us. That telescope does not exist. No signal from it could ever reach us. The image does not exist. The scale does. It made people feel small. But here is what that feeling was. It was the intellectual acknowledgement of smallness. the cognitive registration of a fact. A node in your mental model updated itself. That is different from the thing this script is going to do. There is a specific gap between knowing a thing and processing it. Neuroscientists who study numerical cognition, the way the brain handles magnitude, have found that humans process numbers logarithmically, not linearly. We feel the difference between 1 and 10 more strongly than the difference between 1,000,000 and 10,000,000, even though the second gap is 1,000 times larger in absolute terms. This is important. It means every large number you have ever heard about the universe has been softened by your own brain before it reached you. The brain took the number, placed it somewhere on its logarithmic scale, and filed it next to other large numbers. It did not build the actual structure. It cannot. That is what tonight is about. Start with what is real and specific. A human being is approximately 7 meters tall. The atoms that make up the human being are approximately 0.1 nanometers in diameter. To line up 17 billion hydrogen atoms end to end, you would reach 1.7 meters. 17 billion atoms. Let that sink in for a moment. And that is a line. A human body contains roughly 710 atoms, that is 7 followed by 27 zeros. Every function you perform, every thought, every breath, every heartbeat, is the coordinated behavior of that many individual particles. You do not understand how small we are. Not yet. You do not understand how small we are. Not yet. And that gap between what you believe you understand and what lands is itself part of the story. When the Apollo 8 astronauts took the Earthrise photograph in December 1968, the image of Earth rising above the lunar surface became one of the most reproduced photographs ever taken. It is credited with helping launch the environmental movement. People saw Earth as a fragile, isolated sphere. The planet looked small. But the Moon is 384,400 kilometers away. In the scale of what we are going to describe tonight, the Moon is inside the same rounding error as Earth. The Earthrise photograph, the pale blue dot photograph, every perspective-shifting image of Earth from space, all of them were taken from positions so close to Earth that they register as 0 on the actual scale of the universe. Knowing a fact is a cognitive event. Processing it, building the internal representation that corresponds to the fact, is a different event entirely. You can know that 1 billion is larger than 1 million without ever genuinely feeling that difference. You can know that the universe is 93 billion light years across without that number producing any sensation proportional to what it describes. This script is designed to create the second experience, not the first. It will not fully succeed. Nothing can. But by the time the final chapter closes, the numbers will mean something different than they do right now. Start with what you can hold in your mind. Start with what you can hold in your mind. A human lifespan is roughly 70 to 80 years. In those 70 years, a person might travel 1 million kilometers total. Flying, driving, walking, that is approximately 25 times around the Earth. It sounds like a lot. It is a vanishing fraction of 1% of the distance to the Moon. The fastest unassisted human sprint, Usain Bolt at peak speed, covers approximately 12 meters per second. At that speed, crossing Earth's diameter would take 12 days. Reaching the Moon would take 365 years. Reaching the Sun would take 397 years. These are not useful numbers for understanding cosmic scale. They are useful for establishing that the numbers involved are not in the same territory as anything a body has ever experienced. Human beings are physical objects. We move through space at speeds that are useful for navigating a planet, We perceive distances relevant to navigating a landscape. We evolved in an environment where the relevant scales were meters and kilometers, the height of a tree, the distance to the next water source, the width of a river to cross. Every number in this script is outside that evolutionary range, not a little outside. So far outside that no ratio, no analogy, no scale model fully bridges the gap. Start with what you can hold in your mind. Earth, the planet. The one you are on. Earth's diameter is 12,742 kilometers. If you drove a car at highway speed, 100 kilometers per hour, without stopping, you would need 127 hours to cross that diameter. About 5 days of continuous driving to go from one side of the planet to the other, in a straight line through the core. The circumference of Earth at the equator is 40,075 kilometers. The same car, driving the same speed, would take 400 hours to circle it. 16.5 days without stopping. The circumference of Earth at the equator is 40,075 kilometers. The same car, driving the same speed, would take 400 hours to circle it. 16.5 days without stopping. Consider what that transit would contain. Starting at the equator in the Pacific Ocean east of Kiribati, you would enter South America at Ecuador. You would cross Colombia, Venezuela, Brazil, all the way to the Atlantic coast, then cross the Atlantic, then cross Africa, Gabon, the Democratic Republic of Congo, the vast Central African Basin, then the Indian Ocean, then Indonesia, the scattered islands of the Pacific, and back to where you started. 16.5 days of constant motion. 6 continental landmasses, 4 ocean crossings. Every climate zone on the planet. Every language family. Every ecological biome from tropical rainforest to open ocean. And you would not have gone up or down at all. You would have traced a single horizontal line around the planet's middle. The vertical extent of the biosphere, the layer within which life on Earth exists, is roughly 20 kilometers, from the deepest ocean trench to the highest altitude microorganisms in the stratosphere. 20 kilometers. The circumference of Earth is 40,075 kilometers. The entire vertical range of life on this planet is a thin band representing 0.05% of Earth's circumference. All of life. Every species, every ecosystem. The full depth of the ocean. The full height of the atmosphere where organisms can survive, compressed into a band thinner than the width of a highway on a globe the size of a basketball. That feels large. Now consider, every human being who has ever lived has lived on this planet. Every war was fought here. Every civilization rose and fell here. Every language ever spoken was spoken on this surface. Every piece of music ever composed was composed by a person standing on this rock. The total number of human beings who have ever lived is approximately 108 billion. Every ancestor, every king, every farmer, every child, 108 billion people. And every one of them spent their entire life on a rock 12,742 kilometers wide. If you removed all the space between the atoms in those 108 billion human bodies, the mass that remained, all of human history compressed to its atomic core, would fit inside a volume smaller than a sugar cube. Everything humanity has ever done happened on a rock 12,742 kilometers wide. Everything humanity has ever done happened on a rock 12,742 kilometers wide. Not some of it, all of it. Every war began and ended on this surface. Every treaty was signed here. Every crop ever planted was planted in this soil. Every ocean was sailed on this planet's water. Every mountain ever climbed was on this rock. Every photograph ever taken showed something on or orbiting this particular 12,742 kilometer sphere. Every piece of music ever composed, from the earliest bone flute found in Slovenia dating to 60,000 years ago, to whatever is playing in earphones somewhere on the planet right now, was composed by a person standing, sitting, or lying on this surface. The entire corpus of human knowledge, every library, every database, every hard drive, every cloud server, is physically located on or orbiting this one object. When the first humans left Earth's surface permanently, if that day ever comes, they will be leaving behind the location of every single human experience that has ever occurred. Every memory of every person who has ever lived was formed on this rock. Earth is not where humans happen to be. It is the physical substrate of everything that has constituted human existence for the entire duration of human existence. That rock is 12,742 kilometers wide. That is the reference point. Hold it. The Sun is 109 Earths wide, not 109 times more massive. 109 Earths lined up across its diameter, 1,392,000 kilometers from one side to the other. If Earth sat at the center of the Sun, the Moon's orbit would be inside it. Inside it. More than 1.3 million Earths would fit inside the Sun's volume. Every person who has ever lived, every city, every ocean, every mountain, inside one star. One ordinary, middle-aged, unremarkable star. The Sun is 150 million kilometers from Earth. Light travels at 299,792 kilometers per second, the fastest anything in the universe can move, and that light takes 8 minutes and 20 seconds to reach us. If the Sun disappeared right now, we would not know for 8 minutes. The sky would stay bright, birds would keep singing, then the light would stop. 8 minutes and 20 seconds. Now consider Neptune, the outermost major planet. Neptune is 30 AU from the Sun. 1 AU is 150 million kilometers, the Earth-Sun distance. Neptune is 4.5 billion kilometers from the Sun. Light from the Sun takes 4 hours and 10 minutes to reach it. Voyager 1 was launched on September 5th, 1977. It has been flying ever since, for nearly 50 years. It is currently more than 23 billion kilometers from Earth. It travels at approximately 61,000 kilometers per hour. Voyager 1 is still inside the solar system's gravitational influence. In a scale model where the Sun is the size of a grapefruit in the middle of New York City, Earth is a grain of sand in Philadelphia. Neptune is another grain of sand in Boston. And Voyager 1, after 47 years of flight, is still rattling around in New York's outer boroughs. The entire solar system, every planet, every moon, every spacecraft humans have ever launched, fits inside that grapefruit and its immediate neighborhood. The entire solar system, every planet, every moon, every spacecraft humans have fits inside that grapefruit and its immediate neighborhood. There are 8 planets in the solar system. Confirmed moons. More than 1 million known asteroids. Billions of comets in the Oort cloud. The vast shell of icy bodies extending possibly a quarter of the way to Proxima Centauri. The New Horizons spacecraft flew past Pluto in 2015, 9.5 years after launch, and then continued into the Kuiper Belt, the ring of small bodies beyond Neptune. New Horizons is still travelling. It will take approximately 10,000 years to reach the Oort cloud's inner edge. The outer edge of the Oort cloud, the farthest extent of the Sun's gravitational domain, is roughly 1 to 2 light-years away. In the grapefruit model, the outermost extent of the solar system is roughly 1 to 2 kilometers from the grapefruit, not 4,000 kilometers to Proxima Centauri. a few kilometers to the edge of home. The Sun's gravitational domain, the full sphere within which the Sun's gravity dominates, is enormous by any human standard. It takes light over a year to cross it. But on the scale of the Milky Way, it is a single atom's diameter. The Milky Way contains 200 to 400 billion of these domains, most of them tightly packed in the dense central bulge, spread more loosely in the spiral arms. Each one a solar, some with planets orbiting in zones where liquid water is possible, some with rocky planets of similar size to Earth, all of them invisible from here, all of them folded into the glow of the Milky Way's light, each one a neighborhood, each one unreachable. Voyager 1 has been flying for nearly 50 years. It has not left the solar system's gravitational influence yet. Voyager 1 has been flying for nearly 50 years. It has not left the solar system's gravitational influence yet. Consider what Voyager 1 is. It was launched when disco was still on the radio. Jimmy Carter was President of the United States. The first Star Wars film had been in theaters for 2 months. The personal computer did not exist. The internet did not exist. Mobile phones did not exist. Voyager 1 launched into a world that would become, over the following 47 years, unrecognizable. Every institution it left behind has changed. Every technology it departed alongside is obsolete. Entire countries it flew away from have dissolved and reformed. 2 generations of humans have been born and grown to adulthood since Voyager left Earth. And in all that time, all those decades, all that accumulated human change, Voyager 1 has travelled 23 billion kilometres. At that speed, it would take approximately 73,000 years to reach the nearest star. 73,000 years of continuous flight at the speed of our fastest spacecraft to reach the nearest exit from our immediate neighbourhood. At that speed, crossing the Milky Way would take approximately 1.7 billion years, not the age of the universe, the Milky Way. One galaxy. Ours, the scale of the solar system, is not a stepping stone to the stars. It is a sealed room. The nearest star to our Sun is Proxima Centauri, not a distant star. The nearest one. Our neighbour. Proxima Centauri is 4.24 light-years away. 1 light-year is the distance light travels in a year, about 9.46 trillion kilometres. Proxima Centauri is 40.14 trillion kilometres from Earth. Let that sink in for a moment. In the grapefruit model, where the entire solar system fits in the New York metro area, Proxima Centauri is 4,000 kilometres away. Roughly the distance from New York to Los Angeles and back again. That is the nearest star. Voyager 1, our fastest outgoing spacecraft, travels at 61,000 kilometers per hour. At that speed, it would take approximately 73,000 years to reach Proxima Centauri. 73,000 years. When modern humans left Africa, approximately 70,000 years ago, our entire civilization had not yet begun. Agriculture would not be invented for another 60,000 years. Writing did not exist. The wheel did not exist. Everything that humans have built, discovered, and created since then, all of it, fits inside the travel time to our nearest stellar neighbour. From the surface of Proxima Centauri, our entire solar system would appear as a single star. A bright star. One point of light among thousands. The Sun and Mercury and Venus and Earth and Mars and Jupiter and Voyager 1, all invisible, all folded into that single bright point. Proxima Centauri is our neighbour. It is 40 trillion kilometres away. Proxima Centauri is our neighbour. It is 40 trillion kilometres away. The number 73,000 years is worth sitting with specifically. Human civilization, the whole arc of it, from the first permanent settlements to agriculture, to cities, to writing, to science, to the technological world you are in right now, spans approximately 12,000 years. The oldest confirmed cities are about 7,000 years old. The Roman Empire peaked about 2,000 years ago. The Industrial Revolution began about 250 years ago. All of recorded human history. Every empire, every invention, every work of art, every scientific discovery, every cultural shift. Roughly 12,000 years. Voyager 1, the fastest object humans have ever launched, would complete approximately 1/6 of the transit to Proxima Centauri in that time. At 73,000 years required, human civilization would need to persist for 6 times its entire recorded length to get our probe to the nearest exit. And Proxima Centauri is not a destination, it is a distance marker. It is how far away the first thing outside our solar system is. There is no road, there is no visible path. There is vacuum in every direction, with the nearest other sun 40 trillion kilometers away, and beyond that, 200 to 400 billion more stars, each one separated from its neighbours by similar distances. Proxima Centauri is one star. The Milky Way contains an estimated 200 to 400 billion of them. Let that sentence sit. Not 200 to 400 billion planets. Stars, each one a nuclear furnace the size of a city or a continent or larger. Some of them surrounded by their own planetary systems, and there are somewhere between 200 and 400 billion of them in our galaxy alone. The Milky Way is 100,000 light-years in diameter. 100,000 light-years. Our entire solar system, which already feels incomprehensibly large, is located about 26,000 light-years from the galactic center, roughly in the outer third of one of the spiral arms. In a scale model where the Milky Way is the width of the continental United States, roughly 4,500 kilometers, the entire solar system would be approximately the size of a coffee cup sitting in New York Harbor. The grapefruit is gone. The grapefruit is gone. 200 to 400 billion stars. The range is a range because counting individual stars in a galaxy, even your own galaxy, is genuinely difficult. Stars in the center of the Milky Way are packed so densely that the region is obscured by dust clouds in visible light. Astronomers use infrared, radio, and X-ray observations to penetrate the dusty core and estimate the stellar population. The uncertainty in the total count reflects the limits of this technique. But even the low end, 200 billion stars, is a number that should produce a reaction. If you spent 1 second looking at each star in the Milky Way, you would need 200 billion seconds. That is 6,341 years. All of recorded human civilization has lasted approximately 6,000 years. You would need the entire span from the first Sumerian cities to the present day, spending every second on a different star, to get through one conservative estimate of the Milky Way's stellar population, and most of those stars are invisible from Earth. The naked eye can see approximately 5,000 stars under ideal conditions. The Milky Way's remaining 199,999,995 billion stars are too distant, too faint, or too obscured to resolve individually without instruments. What you see when you look at the Milky Way band overhead is not stars, it is light. The combined glow of billions of stars too far away to see individually, integrated over the full depth of the galactic disk. Tens of thousands of light-years of stars, all folded into a diffuse luminous smear. Each point of that light is a sun, most of them larger than ours. At Voyager's current speed, crossing the full diameter of the Milky Way would take approximately 1.7 billion years. Not million. Billion. The Earth is 4.5 billion years old. The Milky Way is older still. In the entire age of the solar system, Voyager could not cross our own galaxy from one side to the other. Now here is where the scale does something specific. You can see the Andromeda Galaxy with the naked eye on a clear night. It looks like a faint smudge below the constellation Cassiopeia. People have looked at that smudge for thousands of years without knowing what it was. Andromeda is 2.537 million light-years away. The Milky Way, 100,000 light-years across, is now a grain of sand. We have not started yet. We have not started. Here is the scale model in full, before it is replaced. If the Milky Way, 100,000 light-years across, were shrunk to the width of the continental United States, roughly 4,500 kilometers, then the entire solar system would be approximately the diameter of a coffee cup. The distance from New York to Los Angeles and back 4 times. That is the Milky Way. Our coffee cup is sitting somewhere in that model. The nearest star to the Sun is approximately 4 millimeters away from the center of the coffee cup, not the nearest star cluster, the single nearest star. 4 millimeters away in a model where the full Milky Way spans a continent. Every star you can see in the night sky, the entire visible stellar population, would fit within that coffee cup, or within a few centimeters of it. The stars you see from Earth represent the local neighborhood. The Milky Way beyond them, the 99.99% of the galaxy that is too far away to resolve individually, stretches from Texas to Los Angeles to New York to Boston in that model. And then the coffee cup is in a structure the size of a postage stamp. And the postage stamp is in a structure the size of France. And France is 1 grain of sand. We have not started yet. Andromeda is the most distant thing you can see with the naked eye. It was not always known to be a separate galaxy. For most of human history it was catalogued as a nebula, a cloud of gas within our own galaxy. It was not until 1924 when Edwin Hubble analysed Cepheid variable stars in the Andromeda Nebula and calculated their distances that astronomers understood what they were looking at. A separate galaxy, 2,537 million light-years away, containing roughly 1 trillion stars. The light reaching your eye from Andromeda on a clear night left that galaxy 2.537 million years ago. At that moment, on Earth, Homo habilis was walking the African savanna. Modern humans did not exist. The tools being used were stone. Language may not yet have developed in any recognizable form. That light has been traveling ever since. Through the void. In every direction, toward every possible destination, and some of it reached the atmosphere above wherever you are, passed through, and arrived at your eye. The Milky Way and Andromeda are not alone. They are 2 members of what astronomers call the local group, a cluster of more than 54 galaxies bound together gravitationally, spanning approximately 10 million light-years. 10 million light-years. The local group, 54 galaxies, 10 million light-years across, is a neighborhood. In the scale model where the Milky Way is a postage stamp, the local group is roughly the size of France. Andromeda and the Milky Way are approaching each other at 110 kilometers per second. In approximately 4.5 billion years, they will merge. The collision has already begun, in the sense that the gravitational pull between them is already detectable and already shaping both galaxies' outer structures. The local group, 54 galaxies spanning 10 million light-years, is a neighborhood. The universe has millions of neighborhoods. The local group, 54 galaxies spanning 10 million light-years, is a neighborhood. The universe has millions of neighborhoods. The light from Andromeda that is reaching Earth tonight has been traveling for 2.537 million years. It left its source before modern humans existed. It spent the entirety of human prehistory in transit. It crossed the void while our species was still learning to use fire, before we had language, before we had any form of art or ritual. That light encountered nothing on its transit. No obstacle. No medium. Vacuum, the near-perfect emptiness of intergalactic space. For 2.537 million years, it arrived at Earth's atmosphere, passed through it in a fraction of a second, and reached whatever instrument or eye encountered it. The universe is mostly that. Vacuum, emptiness, the galaxies themselves, enormous as they are, occupy an almost negligible fraction of the total volume of space. The filaments of the cosmic web are real structures containing thousands of galaxies, but between the filaments are voids, regions of space, hundreds of millions of light-years across that, contain almost nothing. The universe is not primarily filled with matter. It is primarily filled with space. The matter that exists, the stars, the galaxies, the dust, the gas, the planets, the people, represents a thin tracery of structure in an otherwise nearly empty volume whose scale has no analogue in anything a human being encounters in daily life. The local group is not alone. The local group is not alone. But before expanding to what lies beyond it, it is worth pausing on the fact of the local group itself. 54 galaxies, all of them gravitationally bound together, all of them moving through space together as a unit, falling collectively toward the Virgo cluster, and ultimately participating in the bulk flow of matter toward the Great Attractor, a region of overdense matter toward which a large portion of the observable universe is gravitationally pulled. The Great Attractor is a concentration of mass in the direction of the Centaurus constellation, roughly 250 million light-years away. Its gravitational influence is detectable across hundreds of millions of light-years. The Milky Way, the local group, Laniakea, all of them are moving toward it at hundreds of kilometers per second, caught in its gravitational basin. We discovered the Great Attractor in the 1970s by noticing that galaxies across a large region of sky were moving faster than the universe's general expansion could account for. Something was pulling them. Tracing the direction of that pull led to a concentration of mass large enough to influence the motion of thousands of galaxies. Astronomers could not observe it directly for decades because it sits behind the zone of avoidance, the region of the sky obscured by the dense dust and stars of the Milky Way's own disk. It was not until infrared and radio observations could penetrate that dust that the structures behind it became visible. We live inside a gravitational system that includes structures we could not see from our position until recently. The observable universe is full of things like this. The local group is not alone. On the outskirts of our local group sits the Virgo cluster, a gravitational structure containing approximately 1,300 galaxies, spanning roughly 15 million light-years. The local group is loosely bound to the Virgo cluster's influence, but the Virgo cluster is itself a small part of a larger structure. In 2014, a team led by R. Brent Tully at the University of Hawaii published a paper in the journal Nature. They had developed a new method for mapping the large-scale structure of the universe, tracking the motion of galaxies, and identifying the gravitational basins that govern. What they found was a supercluster. They named it Laniakea. Laniakea means immeasurable heaven in Hawaiian. It spans approximately 520 million light-years. It contains roughly 100,000 galaxies. Its total mass is estimated at 10 solar masses, that is a 1 followed by 17 zeros, measured in units of the Sun's mass. The Milky Way sits near the outer edge of one of Laniakea's filaments. In 2014, for the first time, humans knew the name of the supercluster they live in. Before Tully's paper, we did not have that address. We knew about superclusters in principle. We did not know precisely which one was ours. In a scale model where Laniakea is the size of Europe, roughly 4,000 kilometers across, The Milky Way is approximately the size of a bacterium. A bacterium, not a grain of sand, not a molecule, a single bacterium. A microscopic organism. One of the smallest structures visible under a standard laboratory microscope. That is what the Milky Way, 100,000 light-years across, containing 200 to 400 billion stars, a structure so large that light takes 100,000 years to cross it, is reduced to when placed in a model that shows Laniakea at European scale. Laniakea itself spans 520 million light-years. It contains approximately 100,000 galaxies. Its total mass is estimated at 10 solar masses. It is, by any human standard, incomprehensibly large, and in the scale model where the observable universe is the size of Earth, Laniakea is a grain of sand. The observable universe is a sphere 93 billion light-years in diameter. Laniakea is 520 million light-years in diameter. Laniakea is roughly 0.56% of the observable universe's diameter. In the scale model, a grain of sand in a structure the size of Earth, and the grain of sand contains 100,000 galaxies. In 2014, we learnt the name of the supercluster we live in. We had not known before. Roughly 4,000 kilometers across, the Milky Way is approximately the size of a bacterium. A single bacterium in Paris, in a structure the size of the European continent. In 2014, we learnt the name of the supercluster we live in. We had not known before. In 2014, we learned the name of the supercluster we live in. We had not known before. That fact is worth pausing on. In 2014, not in 1814, not in some era before modern astronomy, scientists published the first definitive identification of which supercluster our galaxy belongs to. Before Tully's paper, astronomers knew superclusters existed. They had catalogued many of them. They did not have a reliable method for drawing the boundaries of these structures. Laniakea's edge is not a wall, it is a gravitational watershed, a boundary defined by the direction in which matter is flowing. On one side, galaxies fall toward Laniakea's centre. On the other side, they fall toward other attractors. Tully's team developed the technique of mapping these gravitational flows by measuring the peculiar velocities of thousands of galaxies, the component of their motion that cannot be explained by the universe's general expansion, and therefore must reflect local gravitational attraction. The result was a three-dimensional map of our cosmic neighbourhood at a scale no one had previously visualised with this clarity. For the first time, humans could see the shape of the structure they inhabit at the 520 million light-year scale. It is a useful reminder that the accumulation of scientific knowledge about cosmic scale is not finished. It is ongoing. The maps keep getting revised. The known keeps expanding. What seems like a ceiling always turns out to be a floor. It is a useful reminder that the accumulation of scientific knowledge about cosmic scale is not finished. It is ongoing. The maps keep getting revised. The known keeps expanding. What seems like a ceiling always turns out to be a floor. The pattern is consistent throughout the history of astronomy. Each era believed it had grasped the structure of the universe. Each era was wrong. The ancient Greeks, with their geocentric model, placed Earth at the centre of a system of crystalline spheres. The outermost sphere bore the fixed stars. Beyond it, nothing. The universe was bound, finite, comprehensible. Copernicus removed Earth from the centre. The Sun became central. The scale of the sphere of fixed stars remained the same. It was still finite, still bounded. When the telescope arrived, the number of visible stars exploded. The Milky Way resolved into individual stars. The universe grew. But the Milky Way was still, for another 3 centuries, assumed to be the entire universe. The spiral nebulae were nebulae, gas clouds within the Milky Way. Then Hubble measured the distance to Andromeda, and the universe grew by a factor of millions overnight. Then the Hubble Deep Field revealed that the blank patches of sky were not blank. Then the galaxy count revised from 200 billion to 2 trillion. Each revision was in the same direction. Each one revealed a universe larger than the previous picture. No revision has ever shown the universe to be smaller than previously thought. The current number, 2 trillion galaxies, 93 billion light-years observable, is almost certainly not final. Future instruments will see further. Future analytical methods will reveal structures current tools cannot resolve. Future revisions will adjust the numbers. The direction of revision is predictable. The current picture is a floor, not a ceiling. 93 billion light-years. That is the diameter of the observable universe, not 13.8 billion. That is the age of the universe in years. The observable universe is larger than 13.8 billion light-years in diameter because space itself has been expanding since the Big Bang. The light from the most distant objects we can observe left them 8 billion years ago, but those objects have since moved much further away as space expanded beneath them. The edge of the observable universe is now approximately 46.5 billion light-years away in every direction. The observable universe contains an estimated 2 trillion galaxies. This number was revised upward dramatically in 2016, when Christopher Consolis and colleagues at the University of Nottingham reanalyzed existing data using new computational models. The previous estimate had been 200 billion. The revised estimate was 2 trillion. The galaxy count increased by a factor of 10 in a single paper. Let that sink in. 2 trillion, each galaxy containing on average 100 to 400 billion stars. The total number of stars in the observable universe is estimated at roughly 10, that is 1 followed by 24 zeros. For comparison, the total number of grains of sand on every beach and desert on Earth is estimated at 7.510. There are roughly 100,000 times more stars in the observable universe than there are grains of sand on Earth. In the scale model where the Milky Way was a bacterium in Europe, the observable universe is the size of Earth itself. Laniakea, 520 million light-years, 100,000 galaxies, is a grain of sand. The Hubble Space Telescope confirmed this in 1995. Astronomers pointed it at a region of sky that appeared completely empty, a patch the size of a grain of sand held at arm's length, a sliver of darkness with no visible stars. They kept the telescope pointed there for 10 consecutive days, letting light accumulate on its sensors. When they processed the image, that empty patch of sky contained more than all Ron galaxies. Every blank spot in the sky is full. The observable universe contains roughly 2 trillion galaxies, each one a collection of hundreds of billions of stars. And we have not seen all of it. And we have not seen all of it. The James Webb Space Telescope, launched in December 2021, has extended this further. In 2022, it released its own deep field image, a patch of sky chosen for its apparent emptiness, exposed for only 12.5 hours. The image revealed thousands of galaxies, some of them from when the universe was less than 600 million years old. Galaxies whose light left them more than 13 billion years ago. Galaxies that no longer look the way they appear in the image, because 13 billion years have passed since that light was emitted. Every image like this delivers the same message. Point and hold the telescope steady, wait long enough. The universe fills the frame. There are no gaps. There are no truly empty regions. There are no gaps. There are no truly empty regions. That statement requires qualification, because the universe does contain voids, regions of space, that are genuinely below average density. Astronomers map these structures. The Boats void, discovered in 1981, is a roughly spherical region approximately 330 million light-years across that contains far fewer galaxies than a typical region of space its size. The KBC void, which the Milky Way sits within, is even larger, an underdense region roughly 2 billion light-years in diameter. But these voids are not empty in any absolute sense. They contain matter. They contain gas, dust, diffuse gas clouds, some galaxies. They are simply less dense than the filaments of the cosmic web surrounding them. The universe has structure at every scale. Below the scale of individual atoms and molecules, quantum fields permeate all of space. The Higgs field, the electromagnetic field, and others extend through every point in the universe without interruption. Even the apparent vacuum of intergalactic space, the regions between galaxy clusters in the depths of the largest voids, is filled with these fields. Particles constantly wink in and out of existence in the vacuum, a consequence of quantum uncertainty. The universe is not a container with objects inside it. It is, at every scale, structured. Every point in space participates in physical processes. The void is not empty. It is less dense than the rest. What we observe, the 2 trillion galaxies, the cosmic web of filaments, the galaxy cluster, is the fraction of this structure that has collapsed under gravity into configurations dense enough to shine with light we can detect. There are no gaps. There are no truly empty regions. The sky is not a dark background with scattered points of light. It is a volume filled with structure in every direction, at every scale, from the nearest stars a few light-years away to galaxies near the edge of the observable universe 46.5 billion light-years away. The reason the sky appears dark at night, why it is not uniformly bright with the combined light of all those stars and galaxies, is that the universe has a finite age and has been expanding. The light from the most distant galaxies is redshifted beyond the visible spectrum, stretched into radio waves and microwaves by the expansion of space over 13.8 billion years. The observable universe is not empty. It is full. We cannot see most of it without instruments calibrated beyond visible light. 2 trillion galaxies, each one full of stars, and we have not seen all of it. The numbers in the previous chapters are correct. Every one of them is verified, measured, published in peer-reviewed literature. The distances are real. The galaxy counts are real. The scale models accurately represent the proportions. And yet something has not happened. You have not processed them. This is not a criticism. It is a statement about the architecture of the human brain. Neuroscientist Stanislas Dehaene, whose research on the brain's number sense has shaped the field of numerical cognition, has shown that humans possess an innate sense of magnitude, but that this sense is approximate, compressed, and we feel the difference between 1 and 10 as larger than the difference between 10 and 100, even though the second interval is objectively 10 times larger. This compression is useful for the environment humans evolved in. A predator that is twice your size is genuinely twice as dangerous as one that is your size. But a predator that is 1 billion times your size and a predator that is 1 trillion times your size are both equally lethal. The brain evolved no circuitry to distinguish them in any practical way. Here is a test. 1 million seconds is 11.57 days. 1 billion seconds is 31.7 years. 1 trillion seconds is 31,709 years. Most people who read those 3 numbers feel roughly the same about all of them. Large, all large. The brain places them in adjacent positions on its magnitude scale. It does not feel the difference. But the difference is enormous. 1 billion seconds ago, the current generation of smartphones did not exist. 1 trillion seconds ago, Homo sapiens had arrived in Europe for the first time. Now apply that same compression to the numbers you have heard tonight. The distance to Proxima Centauri is 40 trillion kilometers. The distance across the Milky Way is roughly 946 quadrillion kilometers. The diameter of the observable universe is approximately 880 sextillion kilometers. These numbers sit in different positions on your logarithmic scale. They do not feel proportionally different. They all feel like the same genre, very large. But they are not proportionally similar. The observable universe is roughly 22 million times larger than the Milky Way. The Milky Way is roughly 24 million times larger than the solar system. The brain was not built to simulate that. It files the numbers. It does not feel their weight. The horrifying truth is not the size of the universe. It is that we are built in a way that prevents us from holding it. The horrifying truth is not the size of the universe. It is that we are built in a way that prevents us from holding it. Dehaene's research specifically documented what he called the approximate number system, a rapid, intuitive sense of quantity that operates throughout the animal kingdom and does not require language or symbolic representation. Rats, pigeons, fish, newborn infants, all of them demonstrate an ability to distinguish between quantities, more and fewer, larger and smaller. But the system compresses. It is logarithmic. The internal representation of the number 1 million is not 1,000 times more intense than the representation of 1,000. They feel like adjacent quantities on a continuum that gets vaguer at the far end. This is the specific reason that scale has to be taught through comparison rather than through raw numbers. 1 million seconds is 11.57 days, 1 billion seconds is 31.7 years, 1 trillion seconds is 31,709 years. Most adults who encounter these three numbers in sequence say the same thing. They knew intellectually that the differences were large, but they did not feel them as proportionally large until they were expressed in relatable units. Now extend this to cosmic scale. The distance from Earth to the Moon is 384,400 kilometers. The distance from Earth to the Sun is 150 million kilometers. Those two numbers feel different, but not 390 times different, which is the actual ratio. The brain files them as close and far. The distance to Proxima Centauri is 40.14 trillion kilometers. The distance across the Milky Way is about 946 quadrillion kilometers. The distance to the edge of the observable universe is about 441 sextillion kilometers. These numbers occupy approximately the same position on the brain's magnitude scale. They all feel like far. The brain has no system that represents the ratio between them, roughly 22 million between Milky Way and observable universe, as an experiential difference. They are all logged as large. This is not a failure of intelligence or education. It is a feature of cognitive architecture. The logarithmic compression that makes numbers above a certain size feel similar is the same system that makes it easy to recognize the difference between a single apple and a pile of 10 apples without counting. It is optimized for the scale of human survival. It was never tested against the scale of the observable universe. What this means practically: every time you have heard someone say the universe is 93 billion light years across and felt something, felt that number, what you felt was your brain's approximate representation of very large. Not the number itself. Not the actual structure. The category. This is why scale comparisons work better than raw numbers. The grapefruit and the grain of sand. the bacterium in Europe, the atom inside a planet-sized Earth. These comparisons bypass the number sense and engage the visual imagination, which can represent proportions. But even those comparisons eventually fail. At some scale, somewhere around the Laniakea to observable universe comparison, the visual imagination also runs out. There is no longer a familiar physical analogue. The comparison becomes an abstraction masquerading as an image. That is the limit. And the limit is reached long before the full scale is described. A light year is 9.46 trillion kilometers. The Milky Way is 100,000 light years across. That is 946 quadrillion kilometers, 946 followed by 15 zeros. The observable universe is 93 billion light years in diameter, 880 sextillion kilometers, 880 followed by 21 zeros. These numbers do not feel different to the brain. They feel like very large. The same number class. The same genre. The brain has no representational system that distinguishes between them as the physics distinguishes between them. What the brain can do is follow the chain of comparisons. One after another, each one making the previous unit disappear. That is what this script is designed to do, not tell you a number, but walk you through the chain until the inadequacy of the brain's number sense becomes itself part of what you understand. The scale cannot be held, but the failure to hold it can be understood. And that understanding is itself a form of comprehension the numbers alone cannot produce. The scale cannot be held, but the failure to hold it can be understood. And that understanding is itself a form of comprehension the numbers alone cannot produce. This is the specific thing this script can deliver, not the experience of holding the scale, which is not available to the human brain, but the experience of watching the scale defeat the brain, one layer at a time. That experience, the specific sensation of a framework of understanding collapsing and needing to be rebuilt at a larger scale, is itself informative. It tells you something about both the universe and about the mind encountering it. Every time the previous scale was rendered inadequate tonight, every time the chapter that established one reference point was overwritten by the next, you were experiencing in miniature what scientists experience over years and decades of working at the frontier of observational astronomy. The expansion of the known, the revision of the scale, the adjustment of everything previously established to fit inside a new, larger context. That process has been ongoing for 400 years. Each generation of astronomers inherited a picture that the next generation expanded. The stars resolved into a galaxy. The galaxy resolved into a neighborhood of galaxies. The neighborhood resolved into a supercluster. The supercluster resolved into a grain of sand in a universe containing 2 trillion of them. The brain cannot hold the final picture. But it can hold the brain cannot hold the final picture. But it can hold the sequence. And holding the sequence is something. It is not the same as holding the scale. But it is a genuine cognitive achievement, the ability to follow a chain of contexts, each one placing the previous inside a larger frame, each one registering as a genuine expansion rather than a repetition of the same large number feeling. That is what astronomers do, not hold the full universe in mind simultaneously. Follow the chain. Proxima Centauri Milky Way Local Group Laniakea Observable Universe. Each step is individually manageable. The accumulation is not. The chain is what remains accessible. The chain is what this script has been. The chain is what remains accessible. The chain is what this script has been. And the chain has a particular property that is worth naming before the script ends. Each link in the chain represents the work of specific people. The distance to Proxima Centauri was measured by Bessels and others using stellar parallax in the 19th century. The structure of the Milky Way was mapped by Harlow Shapley using Cepheid variable stars in the early 20th century. The distance to Andromeda was confirmed by Edwin Hubble in 1924. The Hubble Deep Field was the result of a decision made by Hubble Space Telescope director Robert Williams in 1995, who used his director's discretionary time to point the telescope at a blank patch of sky for 10 days. The Laniakea supercluster was mapped by R. Brent Tully and his team in 2014. The galaxy count revision to 2 trillion was published by Christopher Consolis and colleagues in 2016. Every number in this script came from somewhere. Every measurement was made by someone. Every revision was the result of someone improving a method, building a better instrument, developing a new analytical technique. The universe did not reveal its scale voluntarily. It was measured, one step at a time, over centuries, by people working at the limits of what their instruments and mathematics allowed. That process produced what you heard tonight. A chain of scales, each link added by the effort of specific human beings who spent their careers staring at specific data from specific telescopes, trying to understand what they were looking at. The chain is what remains accessible. The chain is what this script has been. And the chain continues. Every generation adds a link. Every revision makes the picture larger. The chain is not finished. And understanding the sequence, understanding that the scale keeps expanding, that every established reference keeps being placed inside a larger one, that the universe's actual extent remains unknown beyond the observable horizon, is a form of genuine understanding. It is not the understanding of someone who has grasped the full scale. It is the understanding of someone who knows what it would mean to grasp it, and knows that they cannot. That is the honest position. Tonight you have arrived at it. You might be thinking, but the observable universe is not the whole universe. This is true. The observable universe is defined by the limit of what light has had time to reach us from since the Big Bang. Beyond that horizon, there may be, and almost certainly is, more universe. Some cosmological models suggest the full universe may be vastly larger than the observable portion, possibly infinite. And there is the multiverse. The idea, proposed in various forms by cosmologists including Alan Guth and Andre Linde in models of eternal inflation, that our observable universe is one of possibly infinitely many, each one a separate bubble of space-time with potentially different physical constants. So yes, the observable universe may not be the full scale. But here is what that does not do. It does not dissolve the problem. The observable universe is the relevant boundary, not because nothing exists beyond it, but because nothing beyond it can affect us, reach us, or be reached by us. Causally, the observable universe is the universe. Beyond its edge, no signal, no force, no information of any kind can ever arrive here. It is the limit of physical reality as it applies to anything in our history or future. And the comprehension problem has already been completed at this scale. The brain cannot hold 2 trillion galaxies. It cannot hold the ratio of Milky Way to observable universe. Adding unconfirmed multiverses, each one as vast as the one we have already described, does not solve the failure of comprehension. It multiplies a number the brain already cannot hold by a factor the brain also cannot hold. The exit through the multiverse is not an exit. It is more of the same problem, without the empirical foundation. The observable universe is the relevant boundary, and it is already more than enough. On February 14, 1990, Voyager 1 turned its camera toward Earth from 6 billion kilometers away. Carl Sagan had requested the photograph. He had argued for it for years before the Voyager team finally agreed to rotate the spacecraft and take the image on Valentine's Day. The photograph showed Earth as a pale blue dot, a fraction of a pixel, suspended in a beam of scattered sunlight. Earth, 0.1012 pixels. In that 0.112 pixels, 5.5 billion people alive that day. Every nation on Earth. Every building ever constructed, still standing. Every war then ongoing. Every archive, every library, every film ever made. Every living person, and every ancestor whose descendants were still alive. Not 12 pixels. But here is what that image does not show, and what it was always missing. That photograph was taken from 6 billion kilometers away. Voyager 1 was still inside the solar system. The solar system in the grapefruit model is a few city blocks in New York. In the scale model, where the Milky Way is the continental United States, 6 billion kilometers is a fraction of a millimeter. Voyager 1 had not left the room. The famous image of Earth's smallness, the image that made a generation feel the scale of space, was taken from inside the grain of sand. The grain of sand is in a galaxy. The galaxy is one of 54 in the local group. The local group is in Laniakea, one bacterium in Europe. Laniakea is one grain of sand in a universe containing 2 trillion galaxies, and beyond what we can observe, unknown, possibly infinite. Certainly beyond anything the brain can represent. Voyager 1 took that photograph from inside the neighborhood. The nearest exit from the neighborhood is 40 trillion kilometers away. Voyager 1 took that photograph from inside the neighborhood. The nearest exit from the neighborhood is 40 trillion kilometers away. The pale blue dot is one of the most famous images ever made. It has been referenced in eulogies, in political speeches, in philosophy lectures, in arguments about war and environmental destruction. It has been used as evidence that perspective changes everything, that seeing Earth from outside or from far enough outside dissolves petty conflicts and reveals what really matters. All of that is genuinely true at the human scale. Looking at Earth from the moon, or from 6 billion kilometers, does produce a real shift in perspective. The image is real, the effect it produces in viewers is real, but the image was created from inside a margin of error. 6 billion kilometers at the scale of the observable universe is not small. It is not even on the scale. The observable universe is 880 sextillion kilometers across. 6 billion kilometers divided by 880 sextillion is approximately 0.7% of the observable universe's diameter. The pale blue dot was taken from a distance so small, relative to cosmic scale, that it cannot be represented on any diagram that also shows the full observable universe without Earth and Voyager both occupying the same single point. The famous image of Earth's smallness was taken from inside the grain of sand. The pale blue dot is one of the most important photographs in human history, and it shows the beginning of how small we are. None of this was known 400 years ago. In 1610, Galileo turned his telescope on the Milky Way and found that what appeared to be a diffuse glow resolved into individual stars. This was the first evidence that the Milky Way was a structure of discrete stars rather than a luminous band. He could not yet know its extent, its shape, or its position in anything larger. For most of the following 3 centuries, astronomers debated the size and structure of the Milky Way. Many believed it constituted the entire universe. Others suspected the spiral nebulae, faint smudges visible in telescopes, might be island universes, separate galaxies far beyond our own. The question was settled in 1924. Edwin Hubble, using the 100-inch telescope at Mount Wilson Observatory in California, identified individual Cepheid variable stars in the Andromeda Nebula. Cepheids have a known relationship between their pulsation period and their luminosity. They are standard candles, objects whose intrinsic brightness is predictable, allowing their distance to be calculated from their apparent brightness. Hubble calculated the distance to Andromeda. It was vastly farther than any star in the Milky Way. Andromeda was not a nebula within our galaxy. It was a separate galaxy entirely. The universe expanded overnight. Then, in 1995, a Hubble Space Telescope pointed at a blank patch of sky for 10 consecutive days. The Hubble Deep Field. Astronomers expected to find little. Instead, the image revealed more than 3,000 galaxies in a sliver of sky the size of a grain of sand held at arm's length. Every blank area of sky was full of galaxies. In 2016, the galaxy count was revised again. Christopher Consolis's team used new analytical models to account for galaxies too faint for current telescopes to see. Their conclusion: the observable universe contains not 200 billion galaxies, but 2 trillion. The known universe had grown by a factor of 10 in a single scientific paper. Every generation that studied the cosmos believed they understood its scale. Every generation was wrong by at least an order of magnitude. The revision has always been in one direction. The universe measured itself. We did. The universe measured itself. We did. And the measurement keeps changing. In 1995, the Hubble Deep Field produced the 200 billion galaxy estimate that became standard in astronomy textbooks and popular science books for the following 2 decades. That number, 200 billion galaxies, was the received wisdom. It appeared in every documentary, every educational video, every explanation of cosmic scale. Then in 2016, Christopher Consolis at the University of Nottingham and his colleagues published an analysis that revised it upward by a factor of 10. Their method involved analysing the evolution of galaxy number density over cosmic time, asking, given how galaxies form and merge, and given the observed number of galaxies at different distances, how many must have existed throughout the universe's history? Their models predicted roughly 2 trillion. Most of those 1.8 trillion additional galaxies are too faint and too distant for current telescopes to detect. They exist. They are real. We simply cannot see them yet. The revision from 200 billion to 2 trillion happened in a single paper. The known universe grew by a factor of 10. This is not a failure of science. It is science working. Each generation builds better instruments, develops better analytical methods, and extends the known further. The revision is always in the same direction, larger. More, further. The lesson is not that we cannot trust our measurements. The lesson is that our measurements represent the current state of what our current instruments can access, and that state keeps expanding. The universe did not measure itself. We did. And we are not done. There is a reason we are 1.7 meters tall and not 1.7 kilometers. This is not a random outcome. It is a consequence of physics. Carbon-based life operates through chemistry. Molecules bind to each other, break apart, recombine. Enzymes catalyze reactions by physically fitting together with substrates in configurations determined by their 3-dimensional shapes. The relevant length scales for these interactions are nanometers, billionths of a meter. A cell is micrometers across because it needs to contain thousands of these molecular machines working in coordination while remaining small enough that diffusion can transport materials across the cell before they are needed. Neurons, the cells that make thought possible, transmit signals through a combination of electrochemical gradients and electrical pulses. The speed of these signals is limited by the physics of ion channels and membrane capacitance. A brain the size of a planet would be too slow. Signals from one side would take years to reach the other. Coordinated thought would be impossible. A brain the size of a bacterium would lack the complexity. Too few neurons to generate anything recognizable as cognition. The range of body sizes compatible with carbon-based consciousness is not infinite. It has a floor and a ceiling set by physics and chemistry. Human beings are in that range. The specific size we occupy, roughly 1.7 meters, reflects evolutionary pressures acting within those physical constraints. We are not accidentally small. We are necessarily this size. The universe is 93 billion light-years across. We are 1.7 meters tall. We have 70 to 80 years of life. We move through space at the speed of a running animal. That gap is not a mistake. It is the gap between the scale of the cosmos and the scale required for the chemistry of thought. There is no smaller version of us that could think. There is no version of us that is both conscious and galaxy-sized. We exist at approximately the only scale at which minds like ours can exist. The horrifying gap between human scale and cosmic scale is also the gap that makes us possible. The horrifying gap between human scale and cosmic scale is also the gap that makes us possible. This is not a comforting observation. Exactly, it is a precise one. The constraints on the size of conscious organisms are real constraints, not metaphors. Consider what happens at scales significantly smaller than a human being. Below roughly 1 millimeter, thermal noise, random molecular vibrations driven by heat, begins to overwhelm coordinated electrical signals. The electrochemical gradients across neuron membranes, which are what make thought physically possible, require a certain spatial scale to function reliably. Go too small and the signal-to-noise ratio becomes impossible to maintain. Consider what happens at scales significantly larger. Neurons transmit signals at roughly 100 meters per second in fast myelinated fibers. A brain the size of a basketball arena, if it could somehow function, would take seconds for signals to cross from one hemisphere to the other. Coordination at the speed required for real-time decision-making, which is what cognition is at its most practical, would become impossible. A planet-sized brain would be geologically slow. The specific size window in which carbon-based conscious entities can exist is narrow. Organisms within it can process information quickly enough to interact with their environment in real time, using chemistry stable enough to persist across decades, with enough complexity to generate what we call thought. We are in that window. We are approximately the largest conscious organisms this chemistry allows, and approximately the smallest that can sustain the complexity required for the kind of consciousness we have. The gap is not a mistake. It is the necessary gap between the scale of the cosmos and the scale of the only chemistry we know of that can register it. The gap is not a mistake. It is the necessary gap between the scale of the cosmos and the scale of the only chemistry we know of that can register it. There is a further constraint worth naming. Consciousness, whatever it is at the physical level, is plausibly a property of information processing systems of sufficient complexity. The brain processes information through approximately 86 billion neurons, each connected to thousands of others, forming networks whose total synaptic connection count is estimated at around 100 trillion. The speed at which that network operates is determined by the speed of electrochemical signals in neurons, roughly 100 meters per second in fast fibers, much slower in others. At human brain size, the time for a signal to travel from one side of the brain to the other is a few milliseconds. Coordination across the full brain can occur within the time frame of a single perception or decision. Now consider what scaling this up would do. A brain twice the size of a human brain would have cross-brain signal times of tens of milliseconds rather than a few, still workable. A brain the size of a building might have cross-brain times of seconds. A brain the size of a continent, minutes. A brain the size of Earth, hours. A brain the size of the solar system, days. At each scale up, the speed of real-time integration, the property that makes a thought feel like a unified thing rather than a collection of disconnected regional processes, degrades at some scale. The system loses the ability to integrate information across its full extent in time to function as a coherent unit. The universe has no known counterpart to the 86 billion neuron network. It has structures of enormous scale and complexity, but the specific kind of complexity that produces what we recognize as minds, operating at the speed and integration level that produces real-time experience, requires a specific size range. We are in that range. The universe is not. When people genuinely process the scale, not hear the numbers, but feel them, there are two responses. The first is terror. Blaise Pascal, the 17th century mathematician and philosopher, wrote in his Penses, "The eternal silence of these infinite spaces frightens me." Pascal was writing before anyone had measured the true scale of the universe. The Milky Way's extent was unknown. Andromeda was a smudge. The observable universe was not even a concept. And still the silence of the sky above him was enough to produce that line. The terror is legitimate. If nothing in the universe knows we are here, if our entire civilization is less than a mathematical rounding error in the tally of cosmic matter, if every human feeling and every human achievement occurs in a speck of dust that no conscious entity anywhere else will ever observe, then the scale can produce a specific kind of dread. The sensation of insignificance without an audience, of meaning without a witness. This is a real response. It deserves to be named honestly. The second response is liberation. If no cosmic audience exists, then no cosmic judgment exists. The universe is not watching and finding us wanting. There is no external verdict on how human beings should spend the time they have. The scale that makes us invisible also makes us free. What we do here, on this grain of sand, in this 100-year window of individual human life, that is entirely ours to determine. No scale, no distance, no quantity of stars makes it less real from the inside. This is also a real response. It also deserves to be named honestly. Both responses are valid. The script does not arbitrate. What the scale does not change is the texture of being human. The sound of rain on a window is real at human scale regardless of the background. The specific experience of recognizing another person's face is real. Hunger is real. Curiosity is real. These are not diminished by the fact that 2 trillion galaxies exist outside the planet where they occur. The universe is not asking anything of you. What you make of its size is entirely your own. The universe is not asking anything of you. What you make of its size is entirely your own. There is a third response, less commonly named. Wonder, not in spite of the scale, but because of it. The scale that prevents comprehension is the same scale that makes the universe interesting. A universe the size of a soccer field would have nothing surprising in it. Everything would be visible, mappable, knowable in a human lifetime. The fact that 8 billion years of expansion has produced a structure no mind can fully hold, that the universe turns out to be stranger and larger than anything the brain evolved to handle, is itself a kind of evidence about the universe's nature. It is not designed for us. It was not scaled to our comprehension. Its features were not arranged to be legible from the inside. It simply is what it is at the scale it operates at, following the physics it follows. And from one small position on one small rock, organisms built from the same atoms as everything else looked at it and started measuring. That process, the measuring, the calculating, the revising, the building of increasingly accurate maps of a universe that has no obligation to be mappable, is one of the stranger features of the universe itself. It produced, in at least one location, the capacity for self-examination. The universe is not asking anything of you. What you make of its size is entirely your own. But you are already part of the process of the universe knowing itself, whether you chose that role or not. There is one more thing to say about our size. Step outside let your eyes adjust to the darkness. Look up. What you see is a few thousand individual stars, all of them within a few thousand light years of Earth, all of them in the same arm of the same galaxy. The Moon, if it is up, is 384,000 kilometers away. The planets, if any are visible, are points of steady light moving slowly against the stars. The Milky Way, in a dark sky, is a band of diffuse light, the combined glow of billions of stars too far away to resolve individually. This is the universe as it presents itself to human perception. Now consider what is in that view. Every object visible to the naked eye is inside our own galaxy. The faint smudge of Andromeda, which most people cannot see at all, is the only object beyond the Milky Way visible without optical aid. The 2 trillion galaxies, the 10 stars, the 520 million light-year supercluster. None of it is perceptible from this position without instruments. The universe does not know its own extent. The stars in Andromeda do not experience being in Andromeda. The gas and dust in Laniakea's filaments have no knowledge of Laniakea. The entire structure, 93 billion light-years, 2 trillion galaxies, the cosmic web of filaments and voids, exists in complete experiential silence. Except here. On this particular grain of sand, in one spiral arm of one ordinary galaxy, matter organized itself into a form that can ask, how large is all of this? The atoms in your body were forged in stellar interiors and dispersed by stellar explosions over billions of years before assembling into a structure capable of that question. Every atom of carbon in your body passed through at least one star. The iron in your blood was produced in a stellar core more massive than the Sun, in a nuclear fusion process that ended with a supernova. Every atom in your body was once inside a star. The star did not know it. You do. The star did not know it. You do. This is not a poetic statement, it is a precise description of an asymmetry in the universe. Matter is everywhere. The atoms in Andromeda are real. The gas in the filaments of the cosmic web is real. The dark matter halos surrounding every galaxy are real. All of it is physically present, subject to the same laws of physics as everything else. None of it, as far as we know, has any experience of its own presence. The hydrogen atom in the Andromeda galaxy does not experience being in a galaxy. The photon that left Andromeda 2.537 million years ago did not experience the transit. The gas cloud collapsing under gravity to form a new star does not experience the process. The only arrangement of matter in the observable universe that we have direct evidence of experiencing anything, registering its own existence, its own position in space, its own relationship to the scale around it, is this one. Here. The arrangements of matter that constitute conscious organisms on this planet. The experience of being small in a large universe requires a thing that experiences. The universe's scale would exist without any experiencer. But the quality of being horrifying or wondrous or incomprehensible, Those qualities require a mind to encounter the scale. Without a mind, there is space and matter, and the physics connecting them. You are what makes the scale horrifying, not the scale itself. Every atom in your body was once inside a star. The star did not know it. You do. Every atom in your body was once inside a star. The star did not know it. You do. This is a specific and verifiable fact, not a poetic gesture. The hydrogen in your body, most of the hydrogen, was produced in the Big Bang 13,008 billion years ago, when the universe was seconds old and hot enough for protons and neutrons to fuse. That hydrogen drifted as gas for hundreds of millions of years, cooling, gathering, until gravity pulled enough of it together to ignite nuclear fusion. Stars formed. Those stars burned hydrogen into helium, helium into carbon, carbon into oxygen and nitrogen and silicon, progressing up the periodic table through a sequence of nuclear fusion reactions that released energy and built heavier elements. When those stars died, some in supernova explosions that briefly outshone entire galaxies, they scattered those heavy elements into the surrounding space. The carbon in your body, the oxygen, the calcium in your bones, the iron in your blood, all of it was synthesized in stellar interiors and dispersed by stellar deaths. New gas clouds formed from the scattered remnants. Those clouds collapsed into new stars and planetary systems. The solar system formed from such a cloud 4.6 billion years ago. The elements in that cloud, already processed by previous generations of stars, became the sun, the planets, and eventually the material of every living thing on Earth. You are, in a precise and measurable sense, assembled from the debris of stars that no longer exist. Every atom in your body was once inside a star. The star did not know it. You do. Everything described in this script is the part we can see. The observable universe, 93 billion light-years, 2 trillion galaxies, is constructed from matter and energy that interacts with light. That is what we can detect. That is what our instruments measure. But this visible material, everything we have ever seen or will ever see, makes up approximately 5% of the universe's total mass energy content. We do not know what makes up the other 95%. Dark matter accounts for approximately 27% of the universe's total content. It does not emit, absorb, or reflect light. We know it exists because of its gravitational effects. The way galaxies rotate too fast for the visible matter alone to hold them together. The way galaxy clusters bend light from objects behind them more strongly than their visible mass can account for. Every large-scale structure we have described tonight exists inside halos of dark matter that we cannot see. We do not know what dark matter is made of. We know it exists because of its gravitational effects, the way galaxies rotate too fast for the visible matter alone to hold them together, the way galaxy clusters bend light from objects behind them more strongly than their visible mass can account for. Every large-scale structure we have described tonight exists inside halos of dark matter that we cannot see. We do not know what dark matter is made. The search for dark matter particles is one of the most intensive experimental programs in modern physics. Underground laboratories in Italy, the United States, Canada, and China have deployed detectors of increasing sensitivity, hoping to catch the rare interaction between a dark matter particle and an atomic nucleus. The detectors sit deep underground to shield them from cosmic ray background. They are refrigerated to fractions of a degree above absolute zero to reduce thermal noise. They have been running for years. Nothing detected. The Large Hadron Collider at CERN, the the most powerful particle accelerator ever built, was partially designed with the expectation that dark matter candidate particles, particularly the class called weakly interacting massive particles or WIMPs, might be produced in high-energy collisions. Billions of collisions have been analysed. No dark matter candidates have been confirmed. This does not prove dark matter does not consist of particles. The parameter space of possible dark matter candidates is large, and many remain untested. But the most theoretically motivated candidates, the ones that seemed most natural given the structure of physics, have largely been ruled out. We are surrounded by dark matter. We are moving through it right now. Our galaxy is embedded in a dark matter halo that extends far beyond the visible stellar disk, and we cannot detect a single particle of it. The universe is 95% things we cannot see. We live inside the 5% that glows. Dark energy accounts for approximately 68% of the universe's content. It is the term for whatever is causing the universe's expansion. We discovered this in 1998 when two independent teams studying Type Ia supernovae found that distant galaxies were receding faster than expected, that the expansion of space was speeding up. The energy driving that acceleration we call dark energy. We do not know its nature. Normal matter, the atoms, the stars, the galaxies, the 2 trillion galactic structures we have been describing all night, accounts for 5%. We do not know the nature of dark matter. We do not know the nature of dark energy. We do not know what lies beyond the observable horizon. 5%. Everything you have heard tonight, every star, every galaxy, every scale comparison, is 5% of what the universe contains. This is not a metaphor. It is a measurement. The Planck satellite, a European Space Agency mission that operated from 2009 to 2013, produced the most precise map ever made of the cosmic microwave background, the oldest light in the universe. From the detailed patterns in that map, cosmologists derived the most accurate measurements of the universe's composition. The result: 68.3% dark energy, 26.8% dark matter, 4.9% normal matter. Every atom, every molecule, every star, every planet, every gas cloud, every galaxy, every human being, all of it together is 4.9% of what the universe contains. The rest, 95.1%, is forms of mass and energy we cannot directly detect, cannot sample, cannot yet explain at the level of fundamental physics, and have only inferred through their gravitational effects on the 4.9% we can see. We do not know what dark matter is. The most sensitive underground detectors ever built, instruments buried in abandoned mines to shield them from cosmic radiation, capable of detecting individual particle interactions, have found nothing. Decades of search. No direct detection. We know dark matter exists because galaxies rotate too fast for their visible mass to hold them together. We know it exists because galaxy clusters bend light from objects behind them more powerfully than their visible matter can account for. The gravitational evidence is unambiguous. The particle remains a mystery. We do not know what dark energy is. We discovered its existence in 1998 when two independent teams studying exploding stars called Type Ia supernovae found that the universe's expansion was accelerating. Something was pushing galaxies apart faster than gravity was pulling them together. Whatever that something is, it constitutes 68.3% of everything that exists. It has no confirmed particle, no mechanism, no explanation. It is a label for an observed effect whose cause is unknown. The 2 trillion galaxies are markings on the surface of something whose interior we cannot access. 5%. The horrifying truth about our size in the universe is this. The horrifying truth about our size in the universe is this, and it is worth being precise about what the word horrifying means here. Horrifying is not a word chosen for drama. It is not designed to produce distress. It is the accurate word for a specific cognitive experience, the sensation of encountering something that the mind cannot assimilate into its existing frameworks. The experience of a scale that does not fit inside the brain's representational system, even when that system is doing its best. The horizon when you stand on a flat beach is about 5 kilometers away. That is the limit of human visual range at ground level. Everything that matters in daily human life, the buildings, the roads, the people, the weather, occurs within that perceptual bubble. The universe contains 2 trillion galaxies in a volume 93 billion light-years across, and 95% of its mass energy is composed of substances we cannot directly detect or explain. These 2 facts belong to the same reality. They describe the same universe. There is no partition between the 5-kilometer horizon and the 93 billion light-year one. They are both true simultaneously. You are inside both of them right now. The brain that processes the 5-kilometer horizon is the same brain that tried and failed to hold the 93 billion light-year one. Not a different kind of mind. The same one, built by the same evolutionary process, calibrated for the same savannah-scale world. That mismatch, the specific friction between the mind that exists and the universe it finds itself inside, is what horrifying names. Not catastrophe, not danger, the specific cognitive experience of scale that does not fit. We are 1.7 meters tall. We live on a rock 12,742 kilometers wide. That rock orbits a star whose diameter is 109 times Earth's. That star is 26,000 light-years from the center of a galaxy 100,000 light-years across. That galaxy is one of 54 in a cluster spanning 10 million light-years. That cluster is near the edge of a supercluster 520 million light-years across, containing 100,000 galaxies. That supercluster is 1 grain of sand in an observable universe 93 billion light-years in diameter, containing 2 trillion galaxies. And everything we can see, every atom in every galaxy and every structure ever described by any human, is 5% of what the universe contains. The rest is dark matter and dark energy. The rest is unknown. We are 1.7 meters tall. We live on a rock 12,742 kilometers wide. That rock orbits a star inside a solar system that fits inside a grapefruit in a scale model of the Milky Way. The Milky Way is 1 grain of sand in the local group. The local group is a postage stamp in Laniakea. Laniakea is 1 grain of sand in the observable universe. And the observable universe is 5% of what exists. The comprehension failure is not a flaw. The brain was designed to navigate the savannah, to track seasons, to recognize faces, to count threats. It was not designed to hold 10 stars. Acknowledging that the scale exceeds the mind's capacity is not weakness, it is accuracy. The universe is expanding right now. Andromeda is approaching at 110 kilometers per second. The Andromeda-Milky Way merger is one of the few large-scale future events that astronomers can predict with confidence. The trajectory is known. In approximately 4.5 billion years, the 2 galaxies will begin to merge. Despite the collision of 2 structures containing hundreds of billions of stars each, individual stars will almost certainly not collide. The distances between stars are so vast that 2 galaxies can pass through each other without their constituent stars making direct contact. What will happen instead? The gravitational dynamics of both galaxies will be thoroughly disrupted. Stars will be flung into new. The spiral structure will dissolve. What remains will likely be a larger, irregular elliptical galaxy. The night sky at that point, if any organisms are present to observe it, will be transformed. Andromeda will not be a faint smudge. It will be a vast structure spanning a significant portion of the sky. But that merger is 4.5 billion years. Somewhere in the early universe, new stars are forming from the collapse of gas clouds. New stars are forming from the collapse of gas clouds, whose light will take billions of years to reach instruments that may not yet exist. It is all happening simultaneously, in all directions, without pause. You are inside it, not looking at it from outside, not observing it from a distance. Inside it, made of the same matter, subject to the same laws, looking out from one specific position at a specific moment in its 13.8 billion year history. When you look up at the sky tonight, what you will see is the inside surface of the 5% that is visible, the part that interacts with light. The stars you can see are the nearest few thousand, all in your local galactic neighborhood. Beyond them, invisible to the naked eye, the rest of the galaxy, the local group, Laniakea, 2 trillion galaxies, and then the edge of what can reach us. And beyond that, unknown. That is the view from our size in this universe tonight. That is the view from our size in this universe tonight, and it has always been this view. Every human being who has ever lived looked up at the same sky. But the sky they saw was not the same sky we see now. Not because the sky changed, because we learned what is in it. The farmers of ancient Mesopotamia first catalogued the constellations 5,000 years ago looked at the same stars, the same Milky Way band, the same smudge in the direction of Andromeda that almost no one, without foreknowledge, identifies as a galaxy. They had no instruments beyond their eyes. They had no context for what any of it was. What they saw was darkness and light, points of light with no depth, a band of brightness, movement that repeated on predictable schedules, a sky that was useful for navigation, for agriculture, for telling time. Not a sky whose contents they could address individually as objects at specific distances, undergoing specific physical processes. We live in the first centuries of human history, in which the sky has the second kind of meaning, in which Andromeda is not a smudge, but a galaxy 2.537 million light-years away, containing 1 trillion stars, in which the Milky Way band overhead is the interior view of a structure we can now partially map, containing the supercluster whose name we only learned in 2014. The knowledge is recent, it is fragile. Every piece of it required instruments, institutions, methods, and international cooperation that took centuries to assemble and could be dismantled in a fraction of that time. The 5,000-year-old farmer looking at the same sky knew the rhythms. We know the distances. Both kinds of knowledge are partial. Both are real. And it has always been this. Every human being who has ever lived looked up at the same sky. Now you know a little more about what is in it. That is the view from our size, in this universe tonight, and it has always been this view. The farmers of ancient Mesopotamia who first catalogued the constellations 5,000 years ago looked up at the same stars, saw the same Milky Way band, observed the same wandering points of light that are now called planets. They had no instruments beyond their eyes. They had no context for what any of it was. But they looked. The Romans looked. The Polynesians who navigated the Pacific by stars looked. Every culture in every period of human history spent time looking at the same sky, attaching names to the same, building mythologies around the same darkness. What none of them knew, what the people staring at the sky 5,000 years ago had no way of knowing, was that the faint smudge near Cassiopeia was a separate galaxy containing 1 trillion stars, 2,537 million light-years away. That the Milky Way band stretching overhead was the interior view of a structure 100,000 light-years across, that beyond it, in every direction, more galaxies existed than there are grains of sand on every beach on Earth. They looked at the same sky. They did not see the same thing. We see it now because centuries of accumulated measurement changed what the sky is, not what the sky looks like, what it is. The same photons, the same dark background, the same arrangement of points of light, but now located correctly in space and time, now understood to be objects at specific distances with specific compositions undergoing specific physical processes. The sky is different because we know what is in it. That knowledge is recent. It is fragile. It required centuries of work by thousands of scientists across dozens of countries. It required instruments that did not exist until the last few days. It required mathematics developed over centuries by people who never met each other. And it produced this, a picture of the universe so much larger than anything previously imagined that it took several revisions to approach the current estimate. That is the view from our size, in this universe tonight. That is the honest position. Good night.